Greetings, CP Physics. Today we're going to talk about electrical energy, potential, and capacitance. This slideshow is a little long, so I'm sorry ahead of time. Alright, so electric fields and work. In order to bring two like charges near each other, work must be done. In order to separate two opposite charges, work must be done also. So remember that whenever work gets done, energy changes form. So we're looking at this monkey here. I love monkeys. He's bringing a low electric charge towards another electric charge. So as the monkey does work on the positive charge, he increases the energy of that charge. The closer he brings it, the more electrical potential energy it has. When he releases the charge, work gets done on the charge, which changes its energy from electric potential energy to kinetic energy. Kinetic energy means that it's moving. Every time he brings the charge back, he does work on the charge. If he brought the charge closer to the object, it would have more electrical potential energy. If he brought 2 or 3 charges instead of 1, then he'd had to do more work because the charges would be bigger. And that would create more electric potential energy. So electrical potential energy could be measured in joules just like any other form of energy. So remember that energy is in joules. So some more on electric fields and work. Consider a negative charge moving in between two oppositely charged parallel plates, with their initial kinetic energy being 0 and their final kinetic energy being 0, which means it's initially at rest and it ends at rest. So therefore, in this case, the total work done is the change in its potential energy. And for potential energy, we have this equation right here, mass times gravity times height. So here's its initial down here, and here's its final, because we're picking it up. But when we're working with electrical stuff, we're going to have to redo all these letters. And because we call this electrical potential energy, and I should have changed this to a V. I'm sorry, I forgot to do that. Your book uses V. So V, and it's equal to the amount of work done by the electric force caused by the electric field over a distance d, which in this case is the plate separation distance. So you should already know that there is a relationship with the gravitational potential energy formula, specifically Newton's universal law of gravitation, and this electrical stuff, because we talked about that last chapter, but I'll show you a little more. So up here, we have potential energy for gravity. The potential energy for gravity equals mass times gravity times height. So here we can see that equation. So instead of gravitational potential energy, we're talking about electrical potential energy, which we signify with this W here. I'm sorry, that last slide should have been W, not a V. A charge will be in the field instead of a mass. So instead of a mass falling due to gravity, we have a charge being moved through electrical stuff. The field will be an electric field instead of a gravity field. So instead of using little g, we use E. The displacement is the same in any frame of reference, and we can use any variables here that represent distance. We could leave it as h, but since sometimes the orientation of the plates could be different, we're just going to use this d. And putting it all together, we get all this stuff, replacing everything. We get W equals Q times E times D. So, question, what does the left side of this equation mean in words? It means the amount of energy, the W, per charge. So W over Q, energy over charge. So energy per charge. The amount of energy per charge has a specific name, and it's called voltage or electric potential difference. So why the difference? We'll talk about that in a second. So we use this delta V to represent all of this W over Q. So delta V equals W over Q. This W also equals the change in kinetic energy, which we really didn't talk about this year. And the formula for that delta K is 1/2 mv squared. And here we can see in more analogy with the gravity and electric field, gravitational potential energy measured in joules, electric potential energy measured in joules, and how their equations relate to each other. So understanding why we say difference. Let's say we have a proton placed between a set of charged plates. So we start it here. Here's our proton, a little positive guy. If the proton is held fixed at the positive plate, the electric field will apply a force on the proton. Since like charges repel, the proton is considered to have a high potential or voltage, similar to being above the ground. So the higher we have something above the ground, the more potential energy it's going to have. The closer a positive charge is to another positive charge, the more potential it's going to have. It moves towards the negative plate or low potential. So positives like to go to the negatives. High likes to go to low. The plates are charged using a battery source where one side is positive and the other side is negative. So you see we got positives over here and negatives on this side. For example, we could say the positive side is 9 volts and the negative side is 0 volts. So basically the charge travels through a change in voltage. A change in voltage. It goes from 9 over here to 0. That's a change. 9 to 0. Much like a falling mass experiences a change in height. So much like you go from a height of 20 meters and you drop something, it's eventually going to come down to 0 meters. If we had an electron here, it would do exactly the opposite. The electron would, if we started it over here, it would stay on this side. If we started it on this side, it would travel over towards the positive side. So beware, do not get these confused. W is electric potential energy. It's measured in joules. V is electric potential. It's measured in joules per coulomb. V is W over Q. So the units for that, joules for W and coulombs for Q. So the other side of this equation, since the amount of energy per charge is called electric potential or voltage, the product of the electric field and displacement is also voltage. So just like W over Q equals delta V, E times V also equals delta V. This makes sense as it's applied to using those plates that we had before. So here's our change in voltage. We got our 9 up here, our 0 down here. So it's directly proportional to our electric field and the distance between the two. So example, a pair of oppositely charged parallel plates are separated by 5.33 millimeters. A potential difference of 600 volts exists between the plates. What is the magnitude of the electric field strength between the plates, and what is the magnitude of the force on an electron between the plates? So we write down everything we know, because word problems, that's the kind of crap we do. So our distance is 5.33 millimeters. Make sure you convert that to meters. Our voltage is 600 volts. We're looking for E. Charge on an electron is 1.6 times 10 to the minus 19 coulombs. So here's the equation we're going to use. Delta V equals E times D. We have our delta V. We have our D. So we're trying to find E, the electric field strength. So we plug in our numbers. 600 equals E times 0.0053. We divide both sides by 0.0053. And we get... And plug that in the calculator and see what you get. I'll show you the answer in a second. So we also want to know the magnitude of the force of an electron between the plates. So we want to find the force on the electron. And once we know E, we can plug E into this. And there's our E. 207.55 newtons per coulomb. And plugging that E into this guy over here, we get a force on the electron of 1.81 times 10 to the minus 14 newtons. Pretty small force. Now we want to calculate the speed of our protons accelerated from rest through potential difference of 120 volts. Write down everything we know. We're talking about a proton. Charge on a proton is positive 1.16 times 10 to the 19 coulombs. The mass of the proton is 1.67 times 10 to the minus 27 kilograms. Our voltage, our potential difference, is 120 volts. And we're looking for velocity, little v. So we have the equation we used before, WV equals delta V equals W over Q. And W also equals change in kinetic energy, which I said was 1/2 times m times velocity squared over Q. Solving for V gives us this lovely little equation here, which we know everything in, so we can just plug our numbers in. And we get a speed of 1.52 times 10 to the 5 meters per second. Pretty darn fast. We can also find the electric potential of just a point charge, just one charge in space. So here we have a proton, there's our electric field lines coming out. So up to this point we have focused our attention solely on that of parallel plates, like these guys, one plate, two plates, they are parallel. But those are not the only thing that has an electric field. Remember, point charges have an electric field that surrounds them. Like I just said, the electric field for this proton comes out, as we can see from the arrows. So imagine placing a test charge out away from a point charge. So we put a test charge out here. Remember I said test charges are always positive. We'll experience a change in electric potential energy. Will it? Say yes or no right now. I'm coming through the screen and I can hear you. Yes, it will. Thus, it also must experience a change in electric potential as well. So if it has a change in electric potential energy, it's also going to experience a change in electric potential. Remember, potential and potential energy are different things. So using our plate analogy, suppose we had a set of parallel plates symbolic of being above the ground, which has a potential difference of 50 volts and a constant electric field. So electric field is constant, it's going from positive to negative. The distance is also going to be constant. Here's half our distance right here in the center. Half our distance, if it's 50 volts, originally up here at the top. Half the distance is going to have half the voltage. Quarter of the distance, you guessed it, quarter of the voltage. So here's all the different steps. So we want to find the voltage at these different spots, or the change in V at these different spots. So from 1 to 2, we get 25 volts, because 50 to 25, that's a change of 25. From 2 to 3, 0 voltage. It doesn't change at all. From 3 to 4, it's going from here at 25 volts to 4 volts. So the change, or to 12.5 volts. So the change is only 12.5. 25 minus 12.5. Now from 1 to 4, we're going from 50 to 12.5. So 50 minus 12.5 gives us 37.5. Notice that the electric potential does not change from 2 to 3. They are symbolically at the same height and thus have the same voltage. Doesn't matter where on this line these points are, since it's on the same height, the same D, it's going to have the same voltage. The line they are on is called an equipotential line. Equipotential means same potential. So what do you notice about the orientation between the electric field lines and the equipotential lines? Electric field lines go this way, equipotential lines go this way. So they are perpendicular to each other. So let's say you had a positive charge. The electric field lines move away from the charge. The equipotential lines are perpendicular to the electric field lines and thus make concentric circles. So here's our electric field coming out. And at each one of these points where the equipotential lines cross, like that is perpendicular. So that's how we get these circles around there for the equipotential lines. So as you move away from a positive charge, the potential decreases. So here, at V1, we have the highest potential, V2 lower, and V3 the lowest. Now that we have the direction or visual aspect of the equipotential lines understood, the question is, how can we determine the potential at a certain distance from the charge? So we want to know what the potential is at a certain distance from the charge. So let's say this little guy right here. We don't know the potential is for this little green dot. And here's how we do that. So we have our lovely equation. We can change some stuff around. We already should know this from Coulomb's law. And I'm going to introduce a new little sign here. It's the sigma sign. Sigma means the sum of. So voltage, unlike electric field, is not a vector quantity. So if you have more than one charge, you don't need to use vectors. You simply add up all the voltages that each charge contributes, since voltage is a scalar quantity. Warning, you must also use the sign of the charge in this case. In Coulomb's law, like this guy right here, we didn't have to worry about the signs on the charges. But when we're doing this, we have to worry about the signs, positive and negative. So suppose we had 4 charges, each at the corners of a square with sides of equal distance. So all these d's are equal, but the charge strengths aren't. If I wanted to find the potential at the center, right here in the very center, I would sum up all the individual potentials. Sum up these guys. So thus, the distance from corner to corner will equal this. That's how you find the radius of a square. And using the sum sign, we just plug in our numbers. We know what K is, Coulomb's constant, 9 times 10 to the 9 coulombs. All those units that I can't recall right now. And this big Q is the sum of all these charges. So we have positive Q here, which is that guy, 2Q here, which is that guy, negative 3Q, which is that guy, and 5Q, which is that guy. And so we want to know how far each one is because of our R down here. So our distance from each one of these is half of this guy here. So we plug in all of our R's, and we get a whole bunch of different charges that all add up to find the voltage at the center. If they asked us to find the electric field, we would first have to figure out the visual direction, use vectors to break into the electric fields into components, and use Pythagorean theorem, and you gotta do all kinds of crazy crap. And use inverse tangents, a lot of trig stuff. So it's a lot easier to deal with electric potentials, because you can just add up the strength, how far this is, instead of finding all the components of all these different right triangles. And it just gets messy. So using electric potentials is a lot easier. An example, an electric dipole consists of 2 charges, one with positive 12 nanocoulombs and one with negative 12 nanocoulombs, placed 10 centimeters apart as shown in the figure. We want to find the potentials at point A, B, and C. So we use our lovely summation formula. We plug in our K. We plug in how far each charge is. We're trying to find it at A. So point A is 0.4 centimeters from the negative charge. That's why at 0.04 meters over here. And the positive charge is 0.06 meters from point A. So we sum all that up, and you get negative 899 volts. Similarly, for point B, plug in the distance that each one is. The negative is 0.14 meters away, and you get a voltage of that. Voltage at C is going to be 0. Why is it 0? Since direction isn't important, the electric potential at C is 0. The electric field, however, is not. The electric field would point towards the right. That's because we're going to have all these electric field lines coming like this that want to go from the positive to the negative. So at that point C, it's going to point straight to the right. There's several applications we can have for electric potential. So is there any way that we can use a set of plates with an electric field? Of course there is. We can make what is called a parallel plate capacitor and store charges between the plates. So we can actually store charges in here. So a capacitor consists of 2 conductors of any shape placed near one another without them touching. It is common to fill up the region between these 2 conductors with an insulating material called a dielectric. We charge these plates with opposing charges to set up an electric field. So one we put a positive charge on, and one we put a negative charge on. So here's how flashes work in cameras. You can read this at your leisure. I'm trying to make this a little shorter for you. So I want to give you a little schematic on how a battery works. So in the picture below, the capacitor in this is symbolized by a set of parallel lines. So these guys right here, it's parallel lines. And whenever we do get to circuits, remember this because we'll see capacitors in our different circuits that we do. Now, once it's connected to the battery, it'll start charging. And once it's charged, the capacitor will have the same voltage as the battery. So 1.5 volts on the battery means 1.5 volts on the capacitor. Most batteries are like 1.5 volts. So the difference between a capacitor and a battery is that a capacitor can dump its entire charge into a tiny fraction of a second. So it can just get rid of all that charge it has in a second, whereas a battery can't. So that's why the electronic flash on the camera uses a capacitor. So the flash bulbs on your camera, if you go back and read the previous slide, they use a capacitor because it can dump all that charge at one time and make that flash. So the battery charges up the flash's capacitor over several seconds, and then the capacitor dumps the full charge into the flash tube almost instantaneously. So how we measure capacitance? Let's go back and think about plates again. I know you guys love plates. So we have our equation, delta V equals E times D. And this delta V is going to be directly proportional to the electric field. That's only if D is constant. And we know that E is proportional to Q. And so therefore, Q is also going to be proportional to V. So C, we give this a, should be constant, sorry, not content. Proportionality, and C stands for the capacitance. So we have Q, the charge, equals the capacitance times the change in potential difference. Or rearranging this to solve for C, C equals Q over delta V. And the unit for this C is the farad, F-A-R-D, named after a guy named Faraday who did a lot of stuff with electronic junk. Capacitors store energy, we already know this. Anytime you have a situation where energy is stored, it is called a potential. In this case, we have a capacitor with potential energy. We got to change this to VC. So here is a little drawing. The charge goes up, the potential difference goes up too. So suppose we plot a V versus Q graph like I did over here. If we wanted to find the area, we would multiply the two variables according to the equation for area. And the equation for area for this rectangle, this dotted rectangle in here, is the base times the height. So when we do this, we get area equals V times Q. So V is the height, Q is going to be the base. And let's do a unit check. Our voltage for, our units for voltage are joules per coulomb. Charge is coulombs, so if I do joules per coulomb times coulombs, which is V times Q, I get an area with energy units of joules. The coulombs cancel each other out, and we're left with joules. You can also find the potential energy of a capacitor, the W. Since the area under the line is a triangle, the energy equals the area, 1/2 times V times Q. So we're finding this area under the triangle here. Oh, that guy. We're actually finding W. So we can set it up that the energy equals 1/2 times delta V times Q. Here's our V, here's our Q. And we know that C equals Q over V. So we can replace some of this stuff in here. If we solve this equation for Q, we get C times delta V equals Q. So that's why we plugged it in right here. And delta V times delta V is going to give us delta V squared. You can also do it a different way. You can solve this for delta V, make it delta V equals Q over C, and plug it into this guy right here. Times Q, because we have the Q right here. And you get Q squared over 2C equals the energy. Now the most common form of this guy is right here. So the one we're going to use most often is this one that's boxed. Now some more about dielectrics. Dielectric is an insulator. When placed between the plates of a capacitor, it gives a lower potential difference with the same charge due to the polarization of the material. Polarization means positive, negative. It's got two poles. And this increases the capacitance. So if we put a dielectric in between two charged plates, we're going to increase the capacitance that it can hold. You see, like, here's the dielectric. It's an insulator. It's got its molecules all wonky over here. But as we put them in the electric field, they line up with the electric field. So remember that the dielectric is an insulating material placed between the conductors to help store charge. In the previous example, we assumed there was no dielectric and thus a vacuum between the plates. Vacuum meaning there's just air between the plates. That last problem we did. And here's a formula for finding capacitance when we have a dielectric, where K is the dielectric constant. I don't know if we're going to get too many problems with these, but it's good to know. So all insulating materials have a dielectric constant associated with them. Here now you can reduce the area and use the large dielectric to establish the capacitance of 1 farad. So you can make a smaller area, and if you put a good insulating material in here, you can increase the capacitance. So here's some common dielectric constants. Water, it's pretty big. Neoprene, a lot smaller. And then vacuum, get down here, is just 1. So water would make a great dielectric, even though you probably don't want to mix water and electricity too much. They use a lot of glass whenever they do this. Teflon. So if the electric field in a dielectric becomes too large, it can tear the electrons off the atoms, thereby enabling the material to conduct. So this is called dielectric breakdown. So when the dielectric becomes no longer an insulator, no longer dielectric. So the field at which this happens is called the dielectric strength. So here's some common dielectric strengths. So we have some like mica, it's like a stuff that's in sand, like quartz and stuff. Glass, you see they get smaller as they go down. And I believe that's it.